So yeah, thank you for attending my talk today. I hope you enjoy it. I'm going to be talking about an open source project that I worked on that is a future implementation, and also about the tools that I used for building this high performance future. So it might be very useful if you are working with optimizations and want to have high performance code. So just some background on how this came to be. So I now work on the core data libraries team here at Twitter, but previously I was working on the tweets backend service. So as you can imagine, like we have 330 million users, right? And for each read request, we have 5 requests to other services, and 99.99 requests of the requests are reads. So imagine like the scale that we are operating, right? So any savings are considerable in terms of like cap and usage of hardware. So when I started profiling the system, actually the business code didn't even show up on the profiling tools. So that's super funny. Like I didn't see anything like about tweets there. So most of the resources were being used to do RPCs, to run futures and do batching of calls to other services. So the first main target that I started working on was the Stitch free monad. It's something, I don't know if you know Stitch, but it's a way of batching calls to remote services that is more convenient, and it's a free monad. Stitch is not free, open source yet. So there is another project that is very similar that is called Clump. I actually worked on this library at SoundCloud because Stitch wasn't open source, so it's actually just a version of Stitch. And you can have like an idea of how Stitch works, looking at the Clump documentation. So this is one code. It calls a track service and then gets a bunch of tracks given a lot of track IDs. And then for each track from the track service, I get the user IDs of the creators of the track, and then I call the user service to get the users. And then I create like, I have the tracks, I have the users, I create the map that is between users and the actual user. And then I create this enriched track that has the user and the track ID. And that's really, like here it's not so complex, but if you see like calling many services and doing batching, it's really, really complex. So what Stitch and Clump does is allow you to express things as single key computations. So here, for instance, I'm traversing the track IDs, and then I call the track source, get one track, get one user. But this is not going to do 2 calls for each element of the collection. The free monad, the interpreter is going to make calls batched to the external services, to the track service and to the user service. So that like makes the code much, much easier to reason about and much easier to read. But at the same time, it's really hard and challenging to optimize this kind of code. One problem is, if you see the future version, you are calling the track service, and this is creating a future, right? And then you call flat map, this is another future, it's continuation of the future. And then you call user service and map, so you have total 4 futures. And that's like not too much. But with the version using Clump or Stitch, we have to instantiate one Stitch, one Clump for each track source call for a specific track ID, and one for each user source call, right? So you have exponential, I don't know how many tracks we have, like I think the batch size was 20 tweets, so, sorry, 200 tweets, and we would have like 400 allocations here. So that's really, really inefficient. So we did some things. So we switched the internal implementation to use Java, collections, and arrays. That's really terrible, but that's what we had to do. We also use while loops, mutable internals as well, to be able to optimize the execution. We avoided many allocations. One thing that was like the most allocated object in the system was a tuple. In Scala, people normally do like, if I have to do a pattern match, I have 2 objects. I create a tuple with 2 objects and then match them. Just creating this tuple was the most allocated object in the system. So yeah, so we just changed the pattern matching to be a nested pattern matching. And we also created a new implementation of Stitch using arrows. That's something, it's really, really, really interesting. It's probably another talk. But if you want to talk more about this, let me know. I'm going to give you just an intuition of how we use arrows. So there is this tweet I saw actually when I was preparing this talk. Then the person says, free monads should be seen as REPL sessions, not ASTs. That way it's easier to understand that they can't be analyzed in their entirety. Just the first REPL line, or that means everything before the first flat map call. So if you have a task or you have any free monad, you know everything that's happening until there is a flat map call. The flat map body is going to be executed only after the initial composition, the initial AST is executed. So this means that we have to allocate and etc. So the way that we solve this is using arrows. So when we, instead of doing traverse and calling track source, user source, we create an arrow that is a static representation of that transformation. And we use this static representation for building the flat map, something similar to a flat map. So that saves us a lot of allocations. And the second target that is the main topic of my talk today is the Twitter future, to optimize the Twitter future. So the Twitter future is battle tested. It's being used for a long, long time at a really high scale by many types of systems at Twitter and other companies as well. It's really well optimized as well, like it was written by very good engineers. And I decided to go with a clean room approach. So instead of trying to optimize the code itself, I decided to rewrite and actually just get the APIs and try to rewrite and see how I could, like the type of optimizations I could implement. So my goals with this implementation was first, avoid allocations. That's something that was a problem. We have many systems that are GC bound, so allocations are really problematic. Have code that is more friendly to the just-in-time compiler. That was another goal. And also have feature parity with the Twitter future, that is having the same API, have local support and interrupts support as well. So I worked for a while on this project and release. The name is Train.io Future. And there's something interesting. It's in Java 8. So I know that's like mostly a Scala conference, so that's almost blasphemy. But yeah, so you're going to see some Java code. Please don't worry, like it's not going to be terrible, but you're going to see some Java code. So this is just to compare how this new implementation compares to the Twitter future at the time when I released the project. This is a benchmark, and it's very simple. Just create a promise and map, okay? And the map is a cached function, so you have less noise. So this is a profiling session using YorkKit. And I was wondering how many allocations do we have for this transformation using the Twitter future? So the answer is 6 objects and total of 128 bytes. That's a lot. Yeah. And then the new version, it has actually only 2 object allocations. So it's 1 promise and 1 continuation, that is the map, and only 48 bytes of allocations. So that's a huge difference, right? And also in terms of throughput, it's much faster. So the Twitter future can do 19 million operations per second, and the new implementation, I don't know what's happening, sorry. The new implementation can do 72 million operations per second. So it's, I don't know, 4 times, 3 times. So I would like to, just to show you how hard it is to avoid allocations, especially in Scala. Let's say that we have this code here, that is find person. We have a collection of people, we have name, age, and we filter the collection by the name and age, okay? So how many allocations do you think we have here? Is it 1 allocation just for the collection? Is it 4 allocations? Is it 8 allocations? Or is it like any allocations depending on the size of the collection? So who thinks it's 1 allocation? No one? 4 allocations? No one? 8 allocations? Okay, no one. So it must be n allocations, right? Yeah. Okay, cool. So you are actually right. So this is a profiling session of the execution of this method, passing a collection that has only 1 element. So as you can see here, we have 4 allocations. We have the collection and a few other objects being allocated. So where are these allocations coming from? So they end up calling the method filter implementation from the Scala collection implementation. So the first allocation is easy to see. It's the new builder. It's creating the new collection, right? The second allocation comes from this plus equal. It's going to create an immutable list for each element. So it's head and tail, and create like this graph of head and tail objects. And then the other 2 allocations are not really so easy to see. So the other one is the closure that the filter operation is creating. So this is a function that's going to be an object in memory. It's going to have 16 bytes of object header and also 2 pointers, one to the name variable and one to the age variable. So, and each pointer has 8 bytes as well. So you have like some usage of memory here. And the last allocation, can someone spot where this allocation is? Yes, the for loop. So Scala desuggers for loops using for each. So you would expect like something like a while loop, but it's actually this dot for each, and then a function that is the body of the for comprehension. That's the desuggering. And this for comprehension body function is going to have 2 pointers, actually 3 pointers, one to B, one to P, and one to is flipped. So yeah, if you see like it's allocations everywhere and bytes everywhere, and that's something that's really hard to see using Scala code. So now I'm going to talk about some optimizations that I used, and we also implemented for the Twitter future. So the first one is avoiding closures. This is the collect method implemented by the Twitter future, the initial version before the optimization. I don't know if you can see, but there's a line highlighted here that is iterator.next.respond. And this is creating a closure here, right? And this closure has 4 pointers. So it has pointers to fs size, results, count, and p, okay? And this is like, each one is 8 bytes. If you are using compressed ops, if not, it's 16 bytes. And that's a problem because the iterator is going through all futures, and for each future creates one closure with 8 pointers, right? So that's not efficient. Instead of having one object with 5 pointers for each future, we can have only one object that has all the pointers. So that's what the train.io future does. It has this collect promise, okay? And the collect promise has all the structures that we saw before. So it has the results, it's a promise itself. It has the results and also the count and the list of results. So you are saving, instead of allocating this object for each element of the collection, future collection, you allocate only once this object. So the CSL team has been working on these changes, and Vladimir worked on this one, and it led to 50% better throughput and 18 fewer allocations, right? 18% fewer allocations. And that's something interesting because it's only about allocations, the optimization, right? But the gain, like, it's mostly on throughput because allocating things are really expensive. It's not cheap, actually. So, and that's only the work for allocating. There's also the work for garbage collecting and etc. Right? The second one that I'm going to talk about is the merging interfaces technique. That is, here I have the join method. That is, you give it a collection of futures, and it returns a future that will be fulfilled when all futures finish. And it has these 3 structures here. That is a counter, a promise, and an update function. So we can merge all this information into a single object. And that's what the train.io future does. It has the join promise, and then the join promise is a promise itself, has the counter, has the list, but it also is a responder. That is more or less like the closure, but that's the Java version of it. And Jillian from CSL also works on this change, and it's more or less the same result, up to 53% better throughput and 18 better in terms of allocation. So the CSL team has been working on many optimizations. I wrote like a design doc, and they have been delivering many changes, and they are like working on other optimizations as well. And they implemented only the changes that are non-breaking, so they don't change behavior or API. And the results for the tweet service is 16% more tweets served for the same CPU usage and 4 megabytes per second fewer allocations. So that's, if you see like the size of the cluster, it's huge. It's a very good saving. And we are just like halfway. We still have the breaking changes to work on. I also worked on specification for the Scala future. It's very similar to the document that I have for these Twitter futures internally, so you can check it out, tinyurl.com/Scala-future. And it has like many ideas on how we could optimize the Scala future, and Victor Klang is also working on a new version of the Scala future that implements some of these ideas. Cool. So now I want to talk about the tool set that I've been using to do this kind of optimizations. So the first thing is, that's like the best tool for working with performance is benchmarking. And if you are using the JVM, you must use JMH. That's really important. Because you can make so many mistakes if you are not using JMH. It takes care of many things that you could do wrong, right? And also using JMH is not so easy because the just-in-time compiler is always changing your code, and it's hard to understand how it's changing your code. So that's something that you have always to mind when you are doing benchmarking. I would like to share with you some options that I see people sometimes not using with JMH that you can use. So you can enable the built-in GC profiler. That's something that's really useful to see how because sometimes you can have something that's really high throughput and it's generating a lot of garbage. So you have always to mind how much you are generating in terms of allocations. There's this option also to fail the execution if the benchmark fails. I've seen benchmarks doing benchmarks that only check that the code fails super fast, basically, because the default behavior of the JMH execution is only continue executing if there's an exception. So you want to see the exception and see that your code's failing. It's also good to set the JVM args so you can have a stable execution across different environments. One thing that I use is forcing a GC between runs. That's something that's useful. If you have benchmarks that are isolated with very low noise, it's really good to have the GC between runs. And the final option is generating a CSV from your results to make it easier to analyze the results and compare. Another type of tool that I use is profiling. There are many profiling tools out there. The one that I use is a commercial product that is YorkIt. I've been using for, I don't know, 10 years, so I don't know if others are better. I just know this one practically. So you can explore other profiling tools. And it has free licenses for open source projects. That's something that's really useful. But the profiling is at the method level. You can only see if a method is expensive. You can't see what's expensive within the method. That's something that's a big difference. And then there's this other tool that is like for advanced profiling, and it's really, really amazing. I love this tool, but it's also commercial, and there's no free licenses for open source, so that's a problem. That is the Intel vTune amplifier. So it only works for Intel processors on Windows and Linux. There is no Mac support. That's a problem. I actually decided to buy a PC just to run this tool. It's more low level, so you can see how your code interacts with the CPU caches. You can see how your code interacts at the assembly level, for instance, with the processor. And you can see within a method, you can see that there is something in the method that is more expensive than the other things, for instance. And you can also see a source versus assembly code that's being executed by the JVM. Sorry, executed natively using the just-in-time compiler. So the output of the assembly code that's going to be generated by the machine. So I have this example here that is some code from the future implementation that I have in Java. And it's one that's used a lot. And it's not really easy to see what's like the most expensive operation here. First, it's just assigning a variable to current. And then there's like some checking. This is changing the state of the future. And then I was wondering, what is like the most expensive operation of this method? Because the URKit provider was saying that this is expensive, right? And the Intel V2 amplifier said to me that it's actually assigning the state to the current variable. So why is that, right? That's because the state is a volatile variable. So reading the volatile is expensive at the CPU level because it has to do some locking to make sure that the things are consistent at the CPU level. And it's amazing because you can also see the assembly code, right? So you can see exactly what's being executed on the processor level. That's really, really cool. And the last tool that I use is JIT profiling. There's a project that is called JIT-Watch. You can enable options on your JVM to output JIT compilation log, right? And then this tool can read this log. And it's really great. Like there's many features. You can compare the source code versus the JVM bytecode versus the native code, the assembly code. That's really cool. But the only feature that I normally use is one that is really great, that is suggestions. So you can just like open your log and click on suggestions, and it's going to give you like all the suggestions for like, for instance, this method is expensive and it's not being lined because it's the callee, like who is calling this method, is too big. So I could try to see how I can minimize the size of the methods and try to inline this code. I actually tried really hard, but this one's really hard to inline. Yeah, I couldn't. So that's something that's really interesting for profiling your just-in-time compiler output. So just to recap, benchmarking using JMH, profiling, you can use URKit or other tools. Advanced profiling using VTune. I don't know other tools that are similar. I haven't seen any other. And do JIT profiling using JIT-Watch. So that's like my recipe for doing advanced performance work. So now I would like to show you some benchmark results using this new implementation. Here I have just one operation that is mapping a promise. So you have a promise that is something that's not fulfilled yet, just a promise pending. This is the result. The train I/O implementation can do, I don't know how many, 50,000? No, 500,000 operations per second, more or less. And the others are like really not good compared to this one, right? So the Scala future is really not so good. Java async. So Java has two modes, that is the async and sync mode. The async mode is not so great, but the sync mode has good performance, and the Twitter future is not really optimized well for this scenario. And the memory profile, the allocation is also better. As you can see here, like Twitter allocates a lot. Scala allocates more, less than Twitter, and train I/O is like does like very few allocations. And this is the other one is mapping a constant future. This is where the train I/O implementation is much, much better. If you have a constant future, it can be much, much faster. So as you can see here, it's orders of magnitude faster than the others. And allocation is also very low. So what about Scala Z.io that was released yesterday, right? You maybe are asking. So actually, I didn't have much time to analyze the benchmarks and implementation to know like how the implementation is done or if it's correct. But I did some testing to see how it compares with it. And it's actually compatible. I would say that's a good implementation, the Scala Z.io. But there's like some scenarios that train I/O is faster, like 3 times here for this case. But there's some cases like this one. I don't know why, like I have to analyze. I couldn't analyze this one. but this is like the Scala Z is faster, but it's I would say that's a good implementation as well in terms of memory profile and throughput. So, and that's all that I have. Like my team here at Twitter is hiring, so if you wanna talk to me, like come and after the talk we can, yeah, I can say to you like what we are working on, the exciting projects that we are working on. So feel free to grab me after the talk. And if you have any questions, I'm free for questions now.
Thank you so much.
Thank you. Thank you.
Any questions around
I can just ask. So have you considered Visual VM or JVisual VM for profiling?
Yeah, I know about these other tools, and we use it here, them at Twitter, but I have much more experience with YourKit, and I think YourKit has more features, especially for memory profiling. It has like some you can analyze the heap much better with YourKit, I think. Yeah. Any other questions?
Other questions?
No? Okay, thank you.